Hello everyone and welcome to this new video where we're going to see the math behind the recurrent neural network. So if you have a bad memory and already forgot how an RNN works, let's quickly recap. The goal of an RNN is to try and make predictions or classifications where order matters. For example, in texts, time series data, or an audio. The core idea is that at time t, the cell takes current input xt and previous hidden state and computes the new state. That state is the network's memory. The basic RNN cell equation: if we have one layer network, we have the output, which is optional, with this formula: the weight times the last hidden cell plus the bias. So why do we choose the RNNs? It's because they reuse the same weights across time steps, so they share the parameters and can model temporal dependencies. But the main issues is that we have either vanishing or exploding gradients, which leads us to the long short-term memory or the gated recurrent unit networks that we're going to discuss in later videos. So RNN gives the neural network a memory of previous inputs. Let's start with an example. After looking at what we were going to be doing, we're going to do the feed forward step, where we're going to roll the inputs through time, then compute the loss, then perform the backpropagation through time, update the parameters, and repeat. So let's set up the example. The context is that we want to predict the next month's sales in thousands from the last 3 months, and we want to predict the next month forecast. So the input, we have 1, 2, 3 thousands. The target is 5. So we want the recurrent neural network to learn the pattern to predict 5. It's a simple scalar RNN with one hidden size and scalar output. We're going to visualize this later on. So for the initial parameters, we have the weights, biases for both the input layer and the output. Also for the hidden layer, we will use the time h activation function, MSC loss. We have 0.1 learning rate, which is quite big, but for our simple example, it's good. So we're going to perform, as we say, the forward pass, the BPTT, backpropagation through time, and then perform the parameters update using the gradient descent, and then we're going to do a second forward pass. Hopefully the predicted y would move closer to the target, which is 5. Okay, visualizing the network, we can see that the input is 1, 2, 3, and the output is 5. It's a simple scalar recurrent neural network, so we have input hidden and the output. These weights, the wx, are for the input part, so these all share the same weight of 0.5 in the first iteration. This weight h is for this one, for this part, so it's this one, and it's equal to this one, so they are the same from going to this state to this state, and from this state to this state. And the weight y is this one for the output. So we will put the input, multiply by the weight plus bias, get this value, make the activation with tan h, go here using this weight, and this input, and we go here, and then finally we will make the prediction. For the loss, we said we will use the MSE learning rate. We have 0.1. Okay, so let's do the first forward pass. I put here the formulas. Okay, so H0 is 0 because we have nothing here, so it's 0. Okay, at T1 here we multiply the weight of this one, which is 0.5, plus the weight of this part, WH. We said that it's 0.4 multiplied by 0 for the first one because we said we have no previous hidden state, plus the bias. So we get 0.6. We make the activation using tan H and we get 0.537. We do the same, so now we're here, 2 multiplied by the same weight plus the previous value of the hidden state, which is 0.53705, multiplied by this same weight plus the bias. We do the activation function, we get this value. We do the same here, 3 times the weight plus the weight of this part, which is similar to this part, multiplied by the previous hidden state plus the bias. We get this one, and then we perform the activation. We get this value multiplied by this weight here because it's the output layer plus the bias, so we get this value. So from the first iteration with these inputs, biases, weights, we predict that the output would be 0.96 for the next month sales, which is obviously very far from truth because we wanted to get closer to 5. So with the loss we get 16 units of loss here. This is the actual, and we predicted 0.96. These are after the activation, that's why they're not the same values. And now we do the backpropagation. We will use the chain rule obviously, and sum up the contribution over T1, 2, 3 to obtain these numeric gradients. First of all, we would derive the loss over the output 5, so we get this value, and then we go here, so we will derive with the weight and with respect to the weight and biases of the output part, weights and biases, so we get this and this. And next we go here, and because this one depends on this one, we go here, and because this one depends on the previous one, we go here until we reach these this part. So we get these values, and we notice that they are all negative, because negative gradients mean increasing the parameters, since the update of the parameter is the parameter times minus the learning rate plus the gradient. Subtracting a negative increases the value. So the magnitude tells us how strongly each parameter should change. Okay, so now we update the parameters using the formula I just said. The new parameter is the old one, minus the learning rate multiplied by the gradient. So it's straightforward to get these values. So you can see like all the parameters increased from 0.5 to 0.7, from 0.4 to 0.45. The network is being pushed, so the output increases towards 5, because if we remember, the previous output was 0.9, so we need to increase it to get to 5. So it's logical here that they will increase, not decrease, these parameters. So with these new parameters, we do a second forward pass. It's the same thing. We multiply the input by the weight, and the previous one 0 at t1, because there is no previous hidden layer, multiplied by the new weights of the hidden part plus the bias. We get this one, and we apply the 10h activation function. It becomes this value. We do the same thing here and the same thing here also. After getting the value, activation, getting this value, doing the activation. So the output is 2.5 and the loss is 5.91. So we can see that the loss decreased. It was 16 at the first iteration, now it's just 5.9. And also the prediction moved from it was 0.9, if we remember correctly, to 2.5. So we are getting closer to 1. So that's it. If we do many more iterations, we will get closer and closer to 5. The conclusion is that the RNN forward pass propagate input through time. We combine the new input with the previous hidden layer. This is what we call memory. Also, the concept of backpropagation through time, where we unroll the recurrent neural network and we apply the chain rule. So the gradients at each time step accumulate into parameter gradients, and at each part it depends on the previous one, so we go back in time. And after doing the gradient descent update, we move closer to the direction that would reduce the loss. We saw that even with one backpropagation and update, we dramatically got closer to the poor initial guess. But we have to be careful, because this is a very simple example and we use a very high learning rate of 0.1. In real cases, we iterate through many epochs or many sequences, and we use gradient clipping, where like we set like the gradient doesn't get below or higher than a predetermined value. We even use better optimizers like Adam optimizer and other more advanced networks like long short-term memory or the gate recurring units to handle the vanishing and or the exploding gradients problem. So that's it. Thank you for watching this video. If you liked it, please leave a like. Goodbye.